Hello and welcome to Things Explained. This lesson is on demystifying music theory. In this shifting timeline, more people are deciding to pick up music and partake in creation. I am going to lay out a more clear and truthful breakdown of institutional music theory than most would bother entertaining. I will be relying more on the physics and mathematics and ratios of what is going on underneath all of the vocabulary and components of music theory. I hope that this will be empowering to you. Here are some words and phrases coming up soon in this discussion. Circle of fifths. Harmonize. Clash. Chords. Perfect fifth. Perfect fourth. Tetractys. Pythagorean. Tone. Pitch. Note. Flat. Sharp. Half step. Semitone. Chromatic scale. Octave. Hertz. Frequency. A. 440 Hz. A. 432 Hz. Institution. Standard. Arbitrary. 12th root of 2. Tuning. Sound waves. Audible. Inaudible. So, let's get on to it. Sound occurs when pressure vibrations travel through the air at different frequencies. For every second that passes, the amount of waves of pressure that occur forms a rate per second called Hertz. Hertz is sound waves per second. In music, a pitch is any constant rate of sound waves that is audible to human hearing. Pitch and frequency are essentially the same thing, but pitch is most often used in music theory when describing a particular frequency audible of sound. Human audible hearing range is typically from 20 Hz to 20,000 Hz. Anything above or below this range is typically not used, and is not assigned a MIDI number for music composing purposes. It's important to remember, a pitch is not necessarily the same thing as a note. I will make this clear later. A note can have many pitches, but there is only one of each pitch. For example, the note A at a particular frequency, like 440 Hz, can be called a pitch. But a note like A can be played in different heights of pitch and in many different octaves. Notes are tied together in their mathematical relationship with one another, and it's noticeable to the informed student by a trained ear. Here are the 12 different notes that exist in modern institutionalized music. The arrangement of these notes here is called the 12-note chromatic scale. But let's slow down for a moment. Let's open up this topic by just showing you what a note might sound like. The note C at octave 3 sounds like this. Here is a C note at octave 4. That was the same note, but at two different pitches. But let's slow down and talk a bit about what makes an A, and what makes a C, a C. Here's a hint. It's arbitrary. Ever heard of tuning? What one calls an A, in terms of Hertz, is arbitrarily decided, and all other notes are then determined with a grid format based off of that tuning standard. In institutionalized music, we use A4 as 440 Hz. In the early 1900s, A 440 Hz was determined by the industry to be the central reference pitch for the note A in octave 4. Once you designate a central reference pitch for a note, you can then begin to figure out what pitch the other notes will be in the scale, and what all of the octaves will look like. And here's a hint, they all mathematically relate to the reference tuning pitch. For some reason they chose a 440 Hz as the central reference pitch, making it into a nice clean number, even though the music scale we know starts at C, not A. But that's just how it is. An octave is the space between, and including, a particular note, and its frequency double. The music scale we use today, comfortably fits inside the space of an octave. For the remainder of this presentation we are going forward assuming a reference pitch of A, 440 Hz, in the fourth octave. Let's look at this information a little bit closer. The note, G, in the 0th octave, is 24.5 Hz. If you double that frequency, you get 49 Hz, which is also a G, but at a higher pitch, and in the first octave. Everything in between, and including, 24.5 Hz and 49 Hz, is an octave. You can start an octave from anywhere, but you must always end on the double of the frequency whose pitch you started at. Each of those two notes, G, 0, at 24.5 Hz, and G, 1, at 49 Hz, sound like this, and this. Now that we have an octave to use from our most recent example, which stretches between G0 and G1, we can move forward with establishing the knowledge that in between every octave, all 12 notes in the chromatic scale can be found. Here is the sound for G0 through G1, playing all of the notes that come between this octave space. Now maybe you've begun asking yourself, if an octave exists between the space of any particular pitch, and its double, does that mean that we start the scale wherever we want? No, not necessarily. Most of the time you are going to be dealing with the note C as the first note in every octave. So while an octave represents the double of any note, a new octave column will often begin at C and end at B, completing a chromatic scale. So even though the word octave does mean the double, it will often be used also to organize columns in the chart of notes and octaves. Why do we use the C note at the start of our chart to form our chromatic scale columns in our octaves? Well, because a bunch of rich men in powdered wigs decided so, quite a few centuries ago. I mean, you could try to change it, but I doubt any institution would follow your method, as it's not like you have a powdered wig and lots of money. Moving on. So, even though we like to start our columns at C, octaves can still start from anywhere, remember this. An A note at 880 Hz is still an octave higher than the 440 Hz A note. On this chart, our octaves go horizontally, and our notes go vertically. If you double a note's pitch, and keep doing that over and over, the pitch grows exponentially. This means that if you, for example, take the C note at octave 5, which is 523.25 Hz, it's 8 times higher than the C note at octave 2, which is only 65.4 Hz. So the relationship of the frequency of a note, growing into each successive octave, looks kind of like this. This is true for any note as you increase in octaves. So, yes, This means that as you increase in octave, the space inside of each octave grows to more than the last octave. Even the 12 notes in the next, and the next, octaves, get further and further apart from each other in hertz as you move higher in octave. Because this is very strange, and because the octave grows exponentially, the progression of one note to the next needed to have some way to keep it neat and on one page of paper. So some brilliant people decided to look for a way to organize notes better, since each octave is larger and larger. The 12th root of 2. This is a mathematical formula which explains the distance from one note to the next note above it. And it works no matter what octave you are in. The 12th root of 2 uses ratios to make sense of how notes relate to one another in the chromatic scale. It basically means if you take the number 1.05946, and multiply it by any note, and then you multiply the result, again, by 1.05946, and you do this 12 times, you will have doubled your original note to its octave, and found the frequency of every note in between. So let's take a look and run through a simplified example. Let's start with the number 1 as the original note for simplicity's sake. 1 is equal to 1. 1 times 1.05946 equals 1.05946. 1.05946 times 1.05946 equals 1.12246. Then, times 1.12246 by 1.05946. Multiplying the new result again, by 1.05946, once you do this 12 times we reach the double of the frequency of the starting number. In this example, the double of 1 is the number 2. If you look at the column on the right side of this chart, each of the numbers there would represent a note, in a chromatic scale. Now going back to our chromatic scale, moving south, vertically, every note in the scale is 1.05946 times the frequency of the last note that came before it. Isn't that neat? Let's run with that example again, but start with a root number of 261.63 Hz, which is the note C in octave 4. If you follow the same steps from the last example, and roll through it again, instead, with 261.63 Hz as the beginning number, you will develop all of the notes of the entire chromatic scale inside the 4th octave, and you will end up at C again, which starts the next octave. Now that you are armed with this knowledge, I will admit something to you. I said there are 12 notes in an octave or chromatic scale. Although this is correct, technically there can be an infinity of notes within an octave. It's just that institutionally it was determined that we would use just 12 notes, separated by ratios of 1.05946 times the last. Some of you might have heard something about a 432 Hz tuning versus the a 440 Hz tuning. While this is not the place to go deep into that discussion, I will at least show you that if you tune to A4 as 432 Hz rather than 440 Hz as A4, it will sound different, because it is no longer the same pitch. Please listen. If you tune to 432 Hz as A4, you had better make sure your entire band is also tuned to 432 Hz, or else your music won't resonate with the other instruments in the band. There is nothing wrong with changing your pitch tuning for whatever reasons you like, as music is still music, but be prepared to realize that it won't sound like what you expect if you are playing a song written for 440 Hz A tuning. If you'd like to write music in another tuning, that might be a safer bet than trying to play music already written for a different pitch. Because when you change your tuning, it changes the pitch of every note played on that part of your instrument, thus, just about every note in your song. So I'll be moving back to the lesson now. In our chromatic scale, each note is considered to be a semitone, a half step, or one MIDI number away from the next note in the scale. The way music theory is often taught traditionally, places emphasis on the 7 whole notes, without fully explaining the 12-note chromatic scale and the 12th root of 2 spacing. When some teachers jump straight into the 7 whole notes, it can cause intellectual confusion among students who learn differently, because the 7 whole notes are not always evenly spaced apart from one another, like the 12 chromatic scale notes are. Let's hear the whole notes, C, D, E, F, G, A, and B, in sequence. In music theory, E and F are only a half step away from each other. F is 1.05946 times greater in pitch than E. There is no space in between E and F. In music theory, B and C are also a half step away from each other when going from B, the last note in one octave, up to C, the first note in the next higher octave. The C, in this case, is also 1.05946 times higher than the B which precedes it. B and C are only a half step away from one another when entering and leaving an octave. There is no space between the two notes in this case, much like E and F. The remaining whole notes are spaced away from each other by 2 half steps, which leaves one space in between each of the remaining whole notes. These single spaces in between the remaining whole notes are used by sharps and flats. There is no clear mathematical reason for this inconsistent spacing. That's why some students struggle with making sense of it. So I thought it would be a big favor for you to learn the 12-note chromatic scale first, before learning the 7 whole notes. So, next we're going to move on and talk about sharps and flats. These are the mysterious notes that take up the space in between the whole notes that are more than one half step away from one another. A note is said to be sharp or flat when you are in between 2 whole notes. You are said to be sharp when you are 1 half step above a whole note. You are said to be flat when you are 1 half step below a whole note. What this means is that C sharp is also D flat, because C and D are 2 half steps apart. C sharp and D flat share the same pitch and the same note. In addition, the note A sharp is also B flat, as they share the same note and the same pitch. This is because A and B are 2 half steps apart. But when you have 2 whole notes directly next to each other, like E and F for example, you cannot have a sharp or a flat in between them. So there really is no such thing as an E sharp or an F flat. But you can have an E flat, and you can have an F sharp, because there is enough space above F and below E, and the next whole notes are not right up against them, like E and F are flush against each other. The whole note that comes before E is D, and it's 2 half steps away, leaving room for an E flat. The whole note that comes after F is G, and it is also 2 half steps away, leaving room for an F sharp. Next we move on to what the Pythagoreans defined as the tetractys pyramid. The tetractys pyramid is an arrangement of 10 dots, which summarizes the relationship of a note to the relationship of its octave, and the relationship of that octave, or any note for that matter, to its perfect fifth. Then the relationship of that perfect fifth, or any note, to its perfect fourth. The tetractys pyramid is said to be the triangle of musical and cosmic harmony. It works very well to describe harmonic sequences, but the Pythagoreans, arbitrarily, stopped at 10 dots. It's possible to go further, because the next and the next sequences will still be harmonic. Since we already covered octaves in this lesson, let's talk about perfect fifths and perfect fourths. A perfect fifth is a particular ratio of 3 to 2, or 1.5. Its name, perfect fifth, has nothing to do with the actual ratio it represents. Although it is called a fifth in music, it has nothing to do with the ratio, 1/5. We are going to take a look at what a fifth looks like, in terms of mathematics. But before we move on, wait. This one is to the piano players out there, so that they are not confused. I understand that on piano keys, a fifth most often involves moving to the fifth space, counting the root note key, when playing a piano. But that is arbitrary, because it is instrument specific, and it has no bearing to what is going on mathematically in our chromatic scale. Pay attention to the notes actually being played. When discussing fifths and fourths, we will constantly refer to a root note. A root note can be any note in any octave. A root note just serves as a reference note for perfect fifth and perfect fourth calculations. A perfect fifth and a perfect fourth are both ratios that are harmonic with the root note when applied to music. Every note has a perfect fifth and a perfect fourth. Bear in mind, a perfect fifth is not the same thing as 1/5, and a perfect fourth is not the same thing as 1/4. Their names have nothing to do with the ratios they represent. When you take a note, for example, A, 440 Hz, its perfect fifth will be E, 660 Hz. This is because 440 Hz times 1.5 is 660 Hz. Remember that the ratio for a perfect fifth is 1.5 or 3 to 2. The pitch of 660 Hz is harmonic with 440 Hz. Because of how complex it is to design a musical scale, the pitch of 660 Hz, which is the perfect fifth of 440 Hz, is not exactly on the scale, but the closest pitch to it is E5, at 659.26 Hz. To demonstrate the musical harmony and resonance between a root note and its fifth, I will play some tones. Here is 440 Hz tone. Here is 660 Hz tone. And here is 440 Hz and 660 Hz together. Now, let's make a dissonance clash. Here is 440 Hz, with the unharmonic tone 408 Hz, played together. Just notice how they don't pair as smoothly as 440 Hz and 660 Hz. Now, let's go back to hear the 440 Hz, paired with its perfect fifth, 660 Hz again. Moving on, a perfect fourth in this case, is derived from a similar method as the perfect fifth. When calculating for the perfect fourth, pick your root note and then, you must multiply that root note by 1.33, or apply a ratio of 4:3 to your root note. Perfect fourths are also harmonic, and resonate with their root. If you take 440 Hz, and multiply it by 1.33, in order to get its perfect fourth, you will end up with 585.2 Hz as the perfect fourth frequency. I will prove to you now, that they resonate and harmonize with each other. Here is 440 Hz. Here is 585.2 Hz. 585.2 Hz is closest to the note D in the next octave. Now let's hear the root 440 Hz and its perfect fourth 585.2 Hz both at once. Now let's make a clash. Here's 440 Hz with the non-harmonic pitch of 542 Hz played together for a clash. Just for reference, let's hear 440 Hz and its perfect fourth again, 585.2 Hz together, again once more for harmony. Even though 440 Hz is harmonic, with both its fifth and its fourth, its fifth and fourth are not harmonic with each other. Listen here, as 660 Hz and 585 Hz, which are both resonant to 440 but not with each other, are played together and clash. In music theory, chords are when more than one note are played at the same time. Most often using three notes, chords frequently use pitches that are harmonic to each other for vibrant sound. You can expect to see the use of fifths, fourths, and thirds during chord use. Thirds are just like fifths and fourths, except they have a ratio of 5:4 with their root note, or a multiplication of 1.25 to find the frequency of your third from the root. On the chromatic scale and octave chart, perfect fifths always have 6 notes in between the root note and its perfect fifth. On the chromatic scale and octave chart, perfect fourths always have 4 notes in between the root note and its perfect fourth. Let's finish up this lesson laying out some useful information about perfect fifths. If we go to our chromatic scale and octave chart, starting at C, on any octave, in this case, let's use C 65.4 Hz, in octave 2. If you go to its perfect fifth, at G, 97.999 Hz, and then you use G, 97.999 Hz as a root, and go to its perfect fifth, at D, 146.83 Hz, and then you use D, 146.83 Hz as a root, and go to its perfect fifth, at A, 220 Hz, and then you use A, 220 Hz as a root, and go to its perfect fifth, at E, 329.63 Hz, and then you use E, 329.63 Hz as a root, and go to its perfect fifth, at B, 493.88 Hz, and then you use B, 493.88 Hz as a root, and go to its perfect fifth, at F sharp G flat, 739.99 Hz, and then you use F sharp G flat, 739.99 Hz as a root, and go to its perfect fifth, at C sharp D flat, 1108.7 Hertz, and then you use C sharp D flat, 1108.7 Hertz as a root, and go to its perfect fifth, at G sharp, A, flat, 1661.2 Hertz, and you use G sharp, A, flat, 1661.2 Hertz as a root, and go to its perfect fifth, D sharp E flat, at 2489 Hertz, and then you use D sharp E flat, 2489 Hertz as a root, and go to its perfect fifth, A, sharp B flat, 3729.3 Hertz, and then you use A, sharp B flat, 3729.3 Hertz as a root, and go to its perfect fifth, at F, 5587.7 Hertz, and then you use F, 5587.7 Hertz as a root, and then finally go to its perfect fifth at C, 8372 Hertz. What we just did there was we completed a circle of fifths. You start from a note, then you go to its fifth, then you go to that fifth's fifth, and so on, until the sequence takes you back to the same note you started on. A circle of fifths looks exactly like what we just did on the chart, except it's simplified and shown as a clock, like this. So now that I showed you what goes on behind the scenes, you can understand what makes a circle of fifths, a circle of fifths. The circle of fifths moves clockwise when ascending in pitch, and it moves counterclockwise when descending in pitch. In order to go counterclockwise, instead of clockwise, just take the ratio of the perfect fifth, 1.5, and take its reciprocal. 1 over 1.5, which is the same thing as 0.66. When you multiply 0.66 by the root note, you can go counterclockwise in descending perfect fifth pitches. Some people like to make little sentences to help remember the circle of fifths. One common sentence to help memorize the circle of fifths is: Father, Charles, goes down and ends battle. It's a great tool used to memorize a large piece of the circle of fifths. Doing this can help a musician find notes for harmony when composing music. Good job, you made it. Here marks the end of this episode in our series. Hopefully, the ugly, in-depth understanding I've laid out helps to make sense of some of the topics you are learning in music. Thank you for watching Things Explained. If this was helpful to you, please like and subscribe. Have a great day.